Good afternoon, everyone. Welcome to our Lively U Virtual Learning Academy program today. Our presentation is on the COVID vaccine, and I welcome Dr. Tom Milbrot, a physician emeritus, to present this program for us today.
Okay, let me see. Well, I'd like to welcome everybody. I see a lot of familiar names and faces on the participants, and we'll see how this goes with this technology. That's the first time I've ever given a Zoom conference with PowerPoint, so we'll hope things work out pretty well. The presentation I've been asked to give is about the COVID vaccine, a pretty important topic at this time. And let's see, need to see if I can advance my slides. There it goes. Okay, so it's about COVID vaccination, and what I hope to talk about is, first of all, history about vaccination in general, from the and the development of vaccinations, a little bit about vaccination and immunity, and finally do the specific COVID vaccines that we're hopefully going to be using and have started to come into use in just the last few weeks. Vaccination has been around for a few hundred years, and in fact, it starts with this fellow, George Washington, and smallpox, and the epidemic of smallpox that happened 1775 to 1782, and you can see that those years, unfortunately for Washington, coincided with the Revolutionary War. Washington himself had experience with smallpox, and he was just 19 years old. He'd gone with his brother to Barbados since his brother had tuberculosis, and it was hoped that that would be a good thing for his brother's tuberculosis with the warmer climate, but unfortunately exposed Washington to smallpox, and he suffered for a month of being incapacitated with smallpox, and so had a very definite appreciation for the disease. Probably because of the isolation of the colony, smallpox had not been that prevalent among the colonists until additional troops came in from England in order to try to put down the revolution. And they brought smallpox with them. And there was an epidemic in 1776 in Boston that required shutting down much of the city, and various people being quarantined. The troops were quarantined separately from the people. And Washington finally decided by 1778 that he needed to inoculate all of his troops to smallpox. Now, at that time, that wasn't such a benign thing because they did not have smallpox vaccine. However, it had been found out that if one inoculated somebody with the drainage from smallpox sores on somebody that was suffering from the disease, it would give them a case of smallpox, but a less severe case. And it was called variolization. And so finally, by 1778, Washington decided he needed to inoculate all of his troops that he could. Now, this had like a 1% mortality, and many got very sick. But once they were past their sickness, they no longer were subject to smallpox, and Washington did not want his army to have a epidemic coursing through them just a week or two before a major battle. So by mid-1778, pretty much all of the Continental Army had been immunized, And at the very birth of our country, we had our first experiences with both epidemic and with inoculation to help to stop the epidemic. Very soon thereafter, a man in England, actually, in 1796, came up with the discovery that cowpox, which was a very similar disease, but it just infected cows, could be used as an inoculation in people. And rather than having a 1% mortality and many of the people receiving serious illness for a period of time from the inoculation, serious reactions were only 1 in 1,000 or 0.1%. And so this ended up being a very successful program. And in fact, I suspect most of you, and certainly myself, have a scar on their shoulder still from the smallpox inoculation that they got when they were children. My children, however, don't have such a scar because the inoculations for smallpox were so successful that by 1972, it was judged that the risk of getting the inoculation was greater than any risk of getting smallpox, as there wasn't any more in the United States. So vaccination was discontinued in 1972. And through the work of the World Health Organization, by 1980, it was determined there was no more smallpox anywhere in the world. So this was a fantastically successful inoculation program. It worked because smallpox really only infects people. And so after 2,000 to 3,000 years, at least, of having infections and epidemics among people, the virus was eliminated, except for a few samples that remain in laboratories. And that was just the beginning of vaccines. We have many other. When I was a child, we already had vaccines for diphtheria, pertussis, and tetanus, pertussis being what's normally known as whooping cough, or the DPT vaccination that you receive is actually a series of 3 shots. Diphtheria and tetanus are really just toxins, and so those vaccinations are toxoids. They're just a modification of the toxin involved so that it doesn't cause a severe reaction, but it is enough to produce immunity and antibodies to that toxin. Then in the 1950s, scientists and researchers turned their attention to another virus that was a scourge of people, poliomyelitis. And this was a great fear. I know my mother had a great fear of us contracting polio and couldn't wait to have her children get the vaccine, which was first introduced by Jonas Salk in 1955. And this vaccine involved the actual polio virus, which Salk cultured in monkey kidney and then inactivated and turned into a vaccine, which was very successful in preventing polio. And then Sabin discovered a way to attenuate the virus, that is, make it less infectious, but not completely kill it. And that resulted in a vaccine that could be given by mouth. And that is the type of vaccine that is still used today for polio. And this brings up a important property of these diseases that are caused by viruses, and including COVID, in that the virus is a entity that cannot reproduce on its own. You can't take a virus and put it on a culture plate with nutrients like you can with bacteria or yeast and have them grow. They only can grow in actual living cells because they don't have any of the chemical machinery that allows them to reproduce or to produce uh, proteins that make up their shell, and they have to basically hijack the chemical machinery that cells have within themselves to do their own work and take that over to make more copies of themselves and reproduce. Other diseases that we have immunization for as adults include flu. Of course, we have an annual flu vaccine because that vaccine, or the flu virus rather, mutates so much that the vaccine has to be changed on pretty much an annual basis. Uh, we have vaccines for a bacterial disease, pneumococcal pneumonia, that adults need to get at least once. We have a vaccine for the herpes zoster virus, which causes shingles and actually, of course, causes chickenpox in children. And those of us that had chickenpox as children can develop shingles. And this vaccine boosts the immunity to the virus enough that it at least reduces the chances of adults getting shingles. All of these vaccines depend on the body's ability to produce an immune response. And a big part of the immune response is the production of antibodies, which I suspect pretty much everyone has heard of. Antibodies actually can be measured, and that makes them useful because you can measure the antibodies to a particular virus from the blood sample of someone and determine if those antibodies are present, then in fact that person has been exposed to the virus. What antibodies do, and here we have a little graphic to indicate that, if we suppose we have a virus here in the middle of the picture, and the virus consists of just either DNA or RNA, its genetic material inside, plus various proteins that make a shell and also receptors on the outside of the virus. The antibodies, which are represented by these kind of Y-shaped things, because that's actually the way antibodies are shaped. They're proteins produced by the immune system of the body. And they have little regions on the end of the protein that vary from antibody to antibody and fit like a lock and key on proteins on the surface of the virus, and thereby plug them up so that the virus cannot attach itself to cells and infects the cells. And so the antibodies function to basically bind up toxins or virus or bacteria or whatever may be an invader of the body and act as a defense. They also then recruit other features of the immune system, which include cellular immunity, which are lymphocytes or cells in the body that learn how to recognize foreign chemicals or foreign living things that might do harm to the body and basically combat them and neutralize them. So what we have now to deal with is this new virus called COVID. And so I'd like to move now into the topic of COVID vaccines. And these vaccines are for this new virus that has the rather long name of SARS-CoV-2. And this is the official international name that was selected for it. And the reason for it is that it's a coronavirus, and that's where the CoV part of it comes from. And it's related to the virus that caused SARS, a severe respiratory infection. In fact, SARS stands for severe acute respiratory syndrome. And this was a disease that popped up about 18 years ago and was caused by a very similar virus, which was then named SARS-CoV. So this is the second one in that series. I guess that's where the rationale came for the name.
Right. Where'd you go, Park?
The virus.
Was there any mail?
No.
The virus looks under the electron microscope a little bit like this. You've probably seen other pictures more than this cartoon, but the cartoon shows how the virus is structured. It has RNA inside of it, and this carries the genetic code for the virus. It then has a number of proteins that surround and protect this RNA, and then it has a series of spikes on the outer surface that are coded for by a little portion of the RNA genetic code in the virus, and that's what this little arrow is pointing at. These spikes are what make this virus so potent because they allow it to attach to cells in the respiratory tract, in the nose and the throat, and attach very readily, very efficiently, and then enter those cells and hijack those cells and reproduce itself. The other thing that has made this particular virus so pernicious is that unlike SARS, in which case the individuals that became infected with SARS, they became very sick. And before they really became infectious to other people, they were quite sick and coughing a lot. And it was obvious that they had an infection. This made it possible to track those people down and track down their contacts, isolate their contacts, make sure that if they were isolated if they got sick, or that if they didn't get sick, then they could come out of quarantine after a week or so. And the disease was very quickly controlled that way. Another disease that came along maybe 8 years ago called MERS, Middle Eastern Respiratory Syndrome, also had a coronavirus, but it was the same sort of thing. It was SARS had a mortality rate of about 11% for those that contracted it, and MERS had a mortality rate of like 30%. But everybody that was communicable, that could pass it to somebody else, got very sick. And so it was possible to quarantine those sick people and their contacts and control both of those diseases actually very quickly without them spreading very far at all. Our COVID-19 virus is a much nastier thing because most of the people with it don't get very sick. We've had early in the disease many situations, and not so early, even later, where one person who feels just fine can transmit this virus to 50 more people if precautions are not being taken. And many of those 50 people will get very sick and some may die, and that has happened. So this virus has really shut us down. It's made it impossible to have concerts, to have choral groups, eating in restaurants, or drinking in bars has become a very dangerous activity because while the spread can be mitigated by everyone wearing masks and thereby reducing the aerosols from the mouths of people that may be infected but not know it. You can't do that if you're eating in a restaurant or if you're drinking a beer in a bar. And so it's been, and if you're singing, you put out, and you're infected and don't know it, you put out an even greater quantity of this virus. So it's impaired our living incredibly, as I'm sure all of you know. So what's happened at the very beginning of the virus, a year ago, when the virus was first discovered, scientists in China, where it first was discovered and arose, sequenced this RNA in the virus and actually made this available to scientists throughout the world. And this induced many people to start right away, a year ago, starting to make a vaccine. In particular, two companies that have succeeded in making the first very successful vaccine for this, one being BioNTech, which was a very small company in Germany, actually started by two Turkish immigrants to Germany maybe 12 years ago. They developed a vaccine that looked very promising, but they were too small to really be able to produce it. And so they partnered with Pfizer, who had the manufacturing facilities. And in addition, another company, Moderna, in this country, developed a very similar vaccine. And this vaccine is one that is brand new. It's technology for which has only been available for, I don't know, 8 to 10 years maybe. And in fact, this is the very first vaccine that has been developed using this technology, although the companies that developed it had been working on it for some years. So it's like, it's like they were lucky. It's like somebody has said, and I don't really recall who, that luck is when preparation meets opportunity. And so these companies had been preparing for years, developing this technology involving this special kind of RNA called messenger RNA. And along came an opportunity to use it. There's this kind of complicated looking graphic, but let me explain it to you because it's kind of exciting. I hope not all of you will consider it boring, but I find it a really exciting development. The companies actually can manufacture what's called messenger RNA. And what messenger RNA is, it's the kind of RNA that is used by cells to make proteins. It's kind of the final step between DNA, which carries the genetic information and the memory in cells of how to make proteins and make cells, and actually making them. And so these scientists were able to make in quantity this stuff called messenger RNA, which is a rather fragile stuff. It would disintegrate rather quickly in the environment. And so they encapsulate it in with some lipid. And this lipid is just kind of fatty molecules. And this is the kind of their secret sauce and their patented part of the vaccine is these special lipids that these two companies, and the lipid coating for this messenger RNA, which protects it and makes it possible to use it as a vaccine, is different between the two vaccines. But the method is the same. This really tiny, this is what's called a nanoparticle. It's even smaller than a virus that contains the messenger RNA, and in the lipid shield is injected, and then it makes its way to cells within the body of the person being inoculated. And it fuses with the wall of cells, such as lymphocytes in the body. And that messenger RNA passes into the cell, and then it hijacks the chemical machinery of the cell and makes these spike proteins that are on the surface of the coronavirus. And so the cell then proceeds to make these spike proteins for a matter of hours, and the proteins last for a number of days and then appear on the surface of the cell, both the spike proteins that appear on the surface of the coronavirus and and fragments of those spike proteins appear on the surface of the lymphocyte cell and act as a pattern to stimulate the immune system of the person being vaccinated so that they make antibodies to these spike proteins. So without having to be exposed to the virus or even a dead form of the virus, the individual that's inoculated makes antibodies to those proteins on the coronavirus. So this was an entirely new concept. Never had made a successful vaccine from it before, and so it had to be tested. And it was tested the way all drugs and all vaccines are tested, through a series of trials. The first thing you do is what's called phase 1. And in the phase 1 trials, this vaccine or potential vaccine is given to just a very few people. I mean, we don't know if it's going to be toxic, if it's going to have some awful side effects. And so a few brave volunteers get this vaccine. And also then subsequently, if it is a vaccine, the scientists will measure antibody levels in these subjects and see if they make antibodies to the virus that you're trying to vaccinate against, in this case, the COVID-19 culprit virus. And these trials were successful. The volunteers did not get any adverse effects that were of any serious consequence. And then they made antibodies. So the second phase is phase 2, and there the vaccine is given to many more people, like hundreds. It could be that just a few, when you only use a few people, that you missed the side effects. That only, maybe 1 in 100 are going to get an adverse effect that's serious. And so you have to try it on more people. And in addition, when they did the phase 2 trials on these vaccines, they used what we call a placebo group. That is, some of the people got the vaccine and some of them got just salt water in the injection, and really no vaccine at all. And then they measured the antibody levels in all of these people. And what they found is what is shown on this graph. That the tick marks along the baseline are weeks, and so with this was the Pfizer vaccine, was given at the beginning, and then another dose is given after 3 weeks. And this graph is the incidence of the COVID infection, clinical COVID infection in the people that got the vaccine. And this is the incidence of the infection in the people that got the placebo. And so, as you can see, for about a week and a half after the first dose of the vaccine was administered, both the people getting the vaccine and the placebo group that got nothing that was of any potency continued to, some of them developed infections. But then the people that got the vaccine almost no more infections, a few, but almost none, while the people that did not get the vaccine continued to get infections. And again, the group that got the vaccine did not develop any serious side effects. So the next step was finally to go to phase 3 trials where you use tens of thousands of people. So the phase 3 trial for the Pfizer vaccine involved 44,000 total people. And these people were in the United States, in Argentina, in Brazil, and in Germany. And this means that 22,000 of these people got the vaccine, and 22,000 they did not get the vaccine. They just got a shot of saline. And fortunately or unfortunately, the COVID disease was present in all of these countries in very sufficient amounts that plenty of the people that did not get the vaccine got sick. So that, it would be possible to tell the difference between those that were vaccinated and those that weren't. And the efficacy of this vaccine, actually both of them, which has now finished their phase 3 trials, which involved like 2 months of follow-up, the efficacy was 95%. That means that only 5%, as many people that got the vaccine developed any COVID infection at all, as compared to those that did get the vaccine. And that's really amazing. The flu vaccine, for example, is really only like 70% effective. But it's even better than this 95% number. It's true that 5% of the people that got the vaccine developed COVID-19 illness, but they were very mild illnesses. And in fact, of all of the people in these phase 2 trials, phase 3 trials, which between the two vaccines is over 40,000 people, there was one person that developed serious COVID-19 illness. And everybody else, it was mild. So that's really pretty amazing. In addition, I'll talk about the side effects or the adverse effects in a moment, but I wanted to talk about the other vaccines that are on the horizon. There are 2 other vaccines. One is from the Oxford University and AstraZeneca, and the other is from Johnson & Johnson. And these 2 are probably going to be released very soon. They involve the use of an adenovirus, and rather than introduce the messenger RNA directly to the cell, they put it in an adenovirus that cannot replicate within humans. The Oxford people use an adenovirus that causes or that it infects chimpanzees, and the Johnson & Johnson vaccine uses a different adenovirus. But the adenovirus then enters cells. It injects its DNA into the nucleus of the cell. That DNA then makes a messenger RNA, and then the same thing happens. That spike protein that we want the immune system to learn to recognize so it can fight the COVID virus is produced, and the course is the same as the other. This kind of vaccine, or this technique, has only been used for one vaccine that's been approved, and that's the vaccine for Ebola, which was approved like last summer. But it does have predecessor vaccine. The other kind of vaccine that's on the horizon is from Norovax, and it's even a little more complicated. They, in their laboratory, in their factory, they make these spike proteins using actual cells, and actually insect cells. And then the spike proteins are made into little nanoparticles, and an adjuvant is added from the soap bark tree, so that instead of this adjuvant causes the immune system to get kind of stirred up and to recognize the spike protein on the nanoparticles, so that vaccine, so that the vaccine will be more effective and produce a better immune response. This method has been actually used in a couple of vaccines that have been successfully produced, but they're having more trouble with the COVID virus, and actually it's just now entering phase 3 trials. So this vaccine won't be around for a while. The main one we're going to have are these first two that are very remarkably effective and that do have an adverse effect, but it is the adverse effect of most vaccines. That is, like with many flu shots, you'll get some aching where the vaccine happened. You may have some generalized aching the next day, a little bit of low-grade fever and fatigue, but it lasts only 24 to 48 hours. And that's really the only adverse effect that was found during the phase 3 trials. There has been some cases of very severe allergic reactions. They've been very rare. They were not seen in those tens of thousands of people in the phase 3 trials, but they have been seen in a few people that get what's called anaphylaxis, or a severe reaction. These have been almost entirely in people that have had those kinds of reactions before, and they're pretty treatable. But this is the reason that we have people, after getting vaccinated, stay in the vicinity for 15 minutes at least, because these reactions, if they're going to happen within that very short time frame, and then they can be treated. They're the kind of thing that are treated with an EpiPen. Many of the people that get these kinds of reactions get them secondary to insect stings, and then an EpiPen, some epinephrine from an EpiPen, plus then some additional treatment generally takes care, and the reaction usually lasts no more than a day at the most. So this vaccine, we believe, is very important for especially our elderly population to take. And I want to bring to your attention our local statistics for COVID in Wood County. In Wood County, we have so far had almost 10,000 cases. 2,000 of those cases have been in people over 60, 460 over 80. But of our deaths, we've had 153 deaths from COVID. 146 of those have been people over 60. 99 of them people over 80. In other words, almost 1 in 5 of folks over 80 who became infected died as a result of that infection. And all but 7 of our deaths in Wood County have been in people over 60. So the vaccine became available just a few weeks ago, and initially the people vaccinated in Ohio have been healthcare workers exposed to COVID who run a very high risk of contracting COVID, and EMS people, and also people in nursing homes and other congregate care settings that are at high risk. Now, as of this week in Ohio, the vaccine is available to those over 80 years of age who have the greatest risk of death from COVID and the greatest risk of having a very severe case. As of next week, people 75 and over will become eligible. And the following week, people 70 and over. And the following week, people 65 and over. And then once we get everybody 65 and over vaccinated who wants a vaccination, then we will proceed to other people in the population. But the goal, since we have a limited amount of vaccine and a limited means of giving people vaccinations, is to start with the most vulnerable people first and then work our way down. The vaccine is going to be available at multiple sites. Not only the health department, but Wood County Hospital has vaccine this week, as does the Mercy Hospital in Perrysburg. The Kroger pharmacies in Perrysburg and Bowling Green, I understand, have vaccine. And other pharmacies will be having vaccine as time goes on. The idea is to have as many sites as we can so that it makes it easier for people to come and get vaccinated without having to be exposed to a lot of other people. We're going to be asking people to make appointments to get vaccinated so that we don't have like lineups and so that it can be taken care of expeditiously. The health department has a website, woodcountyhealth.org, and at that website, you're going to be able to get up to date information about where the vaccines are going to be available. There's an image on that website. As you click on it, there will be then a bunch of drop down frequently asked question choices where you can find out where vaccinations happen, what will be happening, and also how to contact those places so you can find a place to get vaccinated. Also, United Way, which runs the 211 number where you can get advice about all sorts of issues, healthcare issues, various kinds of needs. They've agreed to supply information as to where you can get vaccinations at their 211 number as well. Wood County Committee on Aging is a source. I understand they've been getting many phone calls. So if you phone them or if you phone the health department, do realize that it may take a while for them to pick up. They'll be wanting to give you information, but a lot of people are calling. And if you have a computer, and obviously if you're on this program, you do have one, the best way is to go to the woodcountyhealth.org website, and I think you should be able to find the information you need there. Finally, the resources I used for this talk, one place with regard to history was from the history.com website, which is the History Channel's website and this was a source of information for about smallpox in the time of the Revolutionary War. And there are some very good articles in the New York Times and the New York Times Online about how the various COVID-19 vaccines work. And this was my source for the various figures that I used in this talk of the COVID virus and illustrations. And there's a lot more detail there than I was able to put in the limited time of my talk about how the various vaccines work. So if that interests you, this series of articles would be a great source, and I think you can maybe see a few of them for free or for a small subscription charge to the New York Times Online. You can read them as much as you like. So that concludes, I think, the things I wanted to talk about. And the plan is to have a question session now. And so hopefully we'll clear up some of the things that you may have had questions about. So I'll stop my little PowerPoint show and answer questions.
So thank you so much, Dr. Milbrat, for sharing that great information with us and providing us with a history on vaccines and helping us to understand the evolution and how it will kind of aid our health. So at this time, I'm going to stop the recording.